All right, now we're going to start. So today we're going to go over instabilities and Chapter 7. And I'm going to actually do things in a little bit different order than the book does, because the book kind of slaps you with the hard thing right away and then does the things that I think are, I don't know, he does it in a different order than I do it. So the first thing I'm going to do is helioseismology. Actually, I'm going to do a super cheap version of this. So we'll put that in quotes because I'm not actually going to get into helioseismology, but I'll talk a little bit about it. And then we'll do, what did I say I was going to do? Then we'll do buoyant instabilities. No, then I'm going to do two states. This one just because I'm going to start with this one because it's relatively quick, but elucidates a lot of things that we're going through with this with all this study. Then we'll do the two-state stuff, the Rayleigh-Taylor and Kelvin-Helmholtz and stuff. We'll do those next because it's hard. And then we'll do convection. And then we'll do Rayleigh-Bernard. And then we'll do genes. And we'll get the genes length. And that's probably going to take us through the week. If I get through all of this, then that will be really cool for me and not useful for you guys if I get through all of this today. So stop me and ask questions when you fall off the bus. Or if the bus looks like it's going over some bulky bits. Okay. Put that over there so we remember what we're doing. So a lot of this chapter is about linearization and the thing that goes along with linearization is superposition. And this is a thing that we haven't talked a lot about, but is really one of the things that underpins why we're going through all of this. So what superposition says is that if I have two solutions to my equation and I add them together, I get another solution to my equation. That's not always true. So with Navier-Stokes, that is not generally true because we have this nonlinear term in the middle that jacks everything up. But when you do have linear operators, then no water here. Then you have superposition. And superposition is really equivalent to linear operators. Or linear equations. And it's also equivalent to all of this Fourier nonsense. So these things are all related to each other because they're all the same thing. So when I have a linear system of equations, I get to do Fourier analysis. That's how it works. If the system's linear, then I can drop in the Fourier analysis, and that gets me my stability. Fourier analysis and superposition, well, the Fourier series is linear. The Fourier transform is a linear transform. If I have two functions, f and g, and I know that f equals the integral of f hat e to the I k x dk. So this is just the Fourier transform of f. F is the Fourier transform of f hat. These are the wave amplitudes, and this is the, in real space, let me be more explicit. This is an x, this is k. If I have another one, g of x, which is equal to integral of g hat of k, e to the I k x dk. So if I have these two Fourier transforms, then f plus g is just the integral of f hat plus g hat e to the I k x d k. So now that doesn't seem like I did very much because, well, yeah, this is a property of integrals. If I add this to this, I get this equation, right? So I didn't say very much, but the fact that I can do this with the Fourier transform is very powerful. That means that in real space and Fourier space, I can make new solutions. If I know one, I can make more. That's really the power of what we're doing, is this relationship between superposition, which you'll hear about a lot when we get to quantum mechanics, because quantum mechanics is all about these beautiful linear operators that do weird stuff, and Fourier analysis. Okay. Just why we're going through all this. Well, let's just do it. So the first thing I'm going to do is the helioseismology bit, mostly because it's short and quick and uncovers physics that I'm really interested in quickly. So we start with the same equation we always start with. So we've got d rho dt plus div rho v equals 0, continuity, and dv dt plus v dot grad v equals minus 1 over rho grad p plus nu del squared v. So we have continuity in Euler's, and we're always going to start with these equations. And maybe we'll start with the internal energy equation when we do convection. We'll talk about that one too. We'll do temperature. But we'll start with continuity in Navier-Stokes. Well, let's look at Navier-Stokes again. Oh, well, we might also have the other forces. For now, let's say we've got some other force on here, because I'm going to throw another force up there right away. Let's assume that we're in one dimension. And it's spherical. Now, this is an oversimplification, and the fact that I'm saying spherical here is why I put helioseismology in quotes over there. Because helioseismology has lots of different modes, not just the radially symmetric one, or the absolutely symmetric one. So we have spherical contractions. So we're just thinking about my system going in and out. So one-dimensional spherical star in hydrostatic. And then 2, we'll perturb it. We'll squish it a little bit. And then 3, we'll see what happens. So we start with our one-dimensional star. What's the equation for that? The equation that describes a sphere of gas is Navier-Stokes again. So let's for a minute ignore the viscosity. The Reynolds number is going to be really, really low. The velocity is going to be really small, but the viscosity doesn't matter. We're not going to have any shear flows. This is radial, right? So we'll ignore that. So let's write down an equation. Let's write down the full derivative, because that's good enough for us for now. Equals what? Minus 1 over rho grad p. Here, let's put the rho over here. Minus g m over r squared. This is a perfectly legitimate equation for gravity. Is everybody on board with this? So this is just what I have up there, but now I've included this gravity term, minus gm over r squared. This is the force due to gravity. So this is cool. So we're going to assume that it's hydrostatic around some rho naught, p naught, and v naught equals 0, and r naught. R naught is the important bit. So we've got some size. So what this means is that rho naught dv naught dt, oh, we said equilibrium, so that part's 0. So, okay, 0 equals minus grad p minus g m over r squared. P naught, r naught. M, mass is conserved. So we're going to assume that the mass doesn't change. Does everybody see how I got here from here? I just put in r naught and p naught, and there's an implicit rho naught in there, and I'm left with this equation. Let's actually write this down a little bit neater because we're going to need it in a second. And let's do this in radial coordinates. Now we've got d by dr. This is the full derivative because it's symmetric. So we said that dp naught dr naught equals minus gm over r naught squared. So we'll need this. That's our background solution. That's the equilibrium. So now, and this is a bit that several people had asked about, we're going to perturb this. We're going to say that r equals r naught times 1 plus delta. Okay, now we wrote this in a slightly different way. I had written it as r equals r naught plus r1 before. This is the same idea. We're just going to parameterize it with 1 plus delta instead of this. So this delta is r1 over r naught, the way we were doing it before. So r equals r naught 1 plus delta. So what's rho? Well, rho equals mr naught, or mr to the minus 3. Might be a 4 pi in there. Might not. So if I plug in 1 plus delta, then I'm left with m r naught to the minus 3, 1 plus delta to the minus 3. And I can series expand this. This is the delta is the variable that I care about, and it's cubed right now, and that's a pain in the butt. I don't like that. That makes my equation hard. Let's make this linear. This turns into m r naught to the minus 3, 1 minus 3 delta. Because that's how the Taylor series of this works. So this is one bit where he says, it is easy to see, but super not. Like, it's not easy to see. You have to do a bunch of math in your head. So I love this book. I think he does a great job, but he pulls this stunt. But every math text does this stunt because you can't spell everything out. You have to leave some stuff. So it is easy to see. Okay, this rho goes to rho naught 1 minus 3 delta. And then P, this one is the hardest one to see. P naught times 1 minus 3 gamma delta. Why is that? Remember what we just said. P equals rho to the gamma because we're assuming that our compression is adiabatic. That means we just flick it and it rings. Yeah.
On that second term, should there be a row?
Here?
No, a line up. On the gm over r squared, when we multiplied the 1 over rho to the other side, do we have to multiply it to that term as well?
No, this is a... no. No, because it's the force from the interior mass. So this is the mass interior to the region. So that takes care of it. Does that make sense?
Yeah.
Because the force that you feel from a dude is just the mass of the interior object. I'll come back to that if that's still not clear in a couple minutes, but we don't need it. Like, it doesn't make a huge difference right now. Because the only thing we're going to perturb is the R. So I'm going to perturb this, and we'll say that, let's see. Maybe I should actually look at the notes instead of trying to do it from memory. So then we're left with dv dt equals minus 1 over rho naught times 1 plus 1 minus 3 delta d Let me actually. Let's do this other thing. I don't want all these things. So dv dt equals minus 1 over rho dp dr minus gm over r squared. Oh no, I'm sorry. Yes, I'm sorry. There should have been a row here. Yeah, this is correct. There should have been a row here if I'd written it that way, but I wanted to write it this way. Sorry. I confused myself and gave you the wrong answer. It should look like this. So yeah, the way I wrote it, there should have been a row there because I had a row here and not one there. So this is the full equation. If we stick in rho, p, and r, go to these over here, then we're left with dv dt equals minus 1 over rho naught times 1 minus 3 delta, dp naught times 1 minus 3 gamma delta, make that better, gamma delta, dr naught 1 plus delta, minus gm over r naught squared 1 plus delta squared. Yeah.
Is that the partial derivative or full derivative of pressure?
Here, because we're now in spherical coordinates, is the full derivative.
The one above it?
Also, it should be the full. So now I've got all these deltas, and I'm just going to Fourier or Taylor a bunch again. So I've got this guy, and this guy. So this gives me, so I'm left with dv dt equals minus 1 over rho naught dp naught dr naught times, let's see, I got a 1 minus 3 gamma delta. I get 1 minus delta here, and a 1 minus, I had a 1 minus delta here and a 1 plus 3 delta here. Why do I get a plus 3 delta? Because it's 1 over 3 delta. So this is 3 delta gamma plus 3 delta from this one minus delta from this one. So we'll simplify that as 1 minus 3 gamma delta plus 2 delta. And then this guy becomes gm over r naught squared times 1 minus 2 delta. Okay, so I plugged in 1 plus delta everywhere that it mattered. I did some more Taylor series, and I'm left with this business. Now here, I'm going to use the background solution. Sorry, I missed 1 over rho naught here. 1 over rho naught dp d rho is minus gm over r naught. This is our equilibrium solution. So I'm just going to use it. So we'll stick that in here. So I'm left with gm over r naught squared times, do a little bit of algebra. I get a 1. So now this thing and this thing are the same. So I'm just doing algebra. This is boring. I'm just going to collect these terms and these terms. And I'm left with a minus 3 delta gamma plus 4 delta. Got a 2 delta and a 2 delta and a minus and a minus. And then we'll simplify this as, we'll say dv dt equals gm over r naught minus. And then 3 delta gamma minus 4 thirds. Okay, So what does this tell us? This tells us a bunch of interesting physics. What is gamma? What does gamma mean to you? It's this thing here. It tells you how squishy the gas is. So if gamma is a very large number, then when I change the pressure, I don't change the density very much. Did I say that? So if I have a very stiff equation of state, that means if I push on it, the density doesn't get very high. If I have a very squishy equation of state, then when I add pressure, the density goes up a lot. Does that make sense? See what this gamma does. Gamma is the squishiness. That's an official term I'm coining right now. It's the squishiness of the gas. What changes gamma? What's in the gas changes gamma. So diatomic gases have different gamma than monatomic gases. But we don't need to worry too much about that. So, well, maybe we do. Gamma is this, and gamma gives you the squishiness. So if my gamma is squishy at 4/3, normally for a monatomic gas, for just hydrogen, gamma equals 5/3. If I can make my gas a little bit squishier, which I can do in some ways, which we'll talk about probably not in this class, then I can make gamma lower. And so this changes. dV/dt is minus gm over r times 3 delta. So if, oh wait, that's a plus there. Right. Oh no, there's a minus. That's right. So as I squish it by a radial delta, then if delta is negative, so I get a little bit more negative, then I'm left with a positive restoring force if gamma is bigger than 4/3, or a negative force if gamma is negative 4/3. So here, if gamma is minus 4/3, then this is negative, and if I squish it with a minus sign, then I squish it this way, then my velocity is large. And if I have the other sign for gamma, then my velocity goes the other way. So here, if delta is negative and gamma is squishy, then this becomes negative, and my velocity response is in the same direction as delta, and it collapses more. So if I've got a star and I squeeze it just a little bit, it'll probably bounce back and oscillate. If it's too squishy and I squeeze it a little bit more, then the squish will just keep squishing and it'll just collapse. Yeah.
So what is delta?
Delta is this. Delta is how I parameterize my perturbation. Let's back all the way back up to the top, because that's a good question. So I'm going to take this star. So I have this star, right, nice and spherical. I'm going to squish it by an amount delta, right? And then the density goes up by this much. The pressure goes up by this much. No, the density goes, yeah. Delta is going to be negative if I squeeze it, right? So density will go up because density is negative, so this term is positive. Pressure will go up by this much. So when I squeeze the star, density and pressure both go up. So then the question is, what happens to the velocity? Does the velocity go in the same direction, or does the velocity go in an opposite direction? And that's what this tells us. Does anybody have any questions about this? Especially questions from the reading that I didn't go over. Does everybody follow how I got here? So we do the same thing that we do a lot. Start off with an equilibrium solution. Perturb everything in a way that's consistent. use Taylor series until you're done. Throw out everything that's big. Then you usually have to do a bunch of algebra. And then you can ask if it's stable. We'll do this again for a different scenario in a second. So the second thing that I want to do is what happens if I have a heavy fluid on top of a light fluid. If I have something heavy on top of something light, the heavy thing squishes the light thing, right? That's how it works. So let's get to it. Let's do that. So we're going to start again with Navier-Stokes and continuity. And we're going to have another kind of cartoon scenario where I have rho prime u prime up here and rho u down here. I've got two states. They could be two layers of a cake. It could be the top and the bottom half of a bottle of water. It could be the ocean and the air over the ocean. It could be all kinds of stuff. So two states, and there's a velocity. And we're going to assume that we're in one dimension, and we'll call this x. We'll call this y. So the first thing that we're going to do is a bit that I skipped, but it's pretty straightforward to talk about, so I'm just going to jump into it. So we're going to assume incompressible. I've talked a little bit about incompressible, what it means. So what that means is also changes in density are zero. What else does that mean? Curl of V is omega. A lot of times you can get yourself into a solution where d omega dt equals 0. I'll show you in a second. I'm just going to say that we do that in a second. So if I take the curl of my equation and I get 0, then the vorticity is constant. So now if the vorticity is constant, then I can say that, well, it's probably 0. And if the vorticity is 0, then I can say that V equals grad phi. Let's stare at that for a second. What's phi? Phi is the potential flow.
Is it not negative?
Oops, yes. So this is like a gravitational potential or a potential energy that you've dealt with. It's the gradient of a thing, gives me the vector that I care about. The nice thing is that phi is not a vector. So this lets us get scalar equations instead of vector equations, which is nice. You have to do a little bit of work to be able to use the potential, but then it's easier to deal with. So what does the potential tell us? The potential tells us a couple of things. So by itself, not a lot, but I know that d phi dx, got to have a minus sign there, is what? Vx. d phi dy is Vy, and d phi dz is Vz, but we'll set z equal to 0 everywhere. So derivatives of this potential phi are my velocity components. So we'll think about phi as the velocity, even though it's really not. I'm not actually going to say that, but it gives us the velocity. Okay, let's take this and we can take Navier-Stokes and rewrite it. Uh-oh, my notes are out of order. No, they're not. Let's see, what's the easiest way to describe this? well, we take this and we drop this in, and we're left with d by dt of grad phi plus grad 1/2 v squared. This comes from taking the curl of this term. Oh, we're okay, so we're gonna make two assumptions that I forgot to say aloud. Incompressible and adiabatic. These are super common assumptions for one to make when dealing with fluids because they're usually pretty good. Adiabatic just means the changes are fast. That just means it's fast enough that heat doesn't flow. So we don't have to worry about thermal conduction. Also, being adiabatic means 1 over rho grad P. I can bring the P in there because I know that it, because the other term goes away when we took the curl. I get minus grad P over rho. Now I need a force in here plus F. What force should I use? I'm going to use minus grad big phi. Well, big phi is the gravitational potential. So now I got two phi's running around. That's a little annoying. How does big phi work? Well, big phi, grad big phi is minus grad big phi is the gravitational acceleration. That's why we define phi. That's why we define a potential. Because just like this, the force is the gradient of a potential. That's how we get to this guy here. So the gravitational acceleration is minus big grad phi. Also, I know that del squared big grad phi is 4 pi g rho. This is equivalent to F equals gm m over r squared. But I'm not going to show you that right now. This is Poisson's equation. This is how gravity works. The only thing that I need, I'm only saying that because I'm going to need it later. This is the bit that I need now. And really, I don't even need the fact that it's grad of a potential. We're just going to call it G. Because I have gradients on all three of my terms, or on all of my terms now, so that I can put everything under a gradient and say that everything has to be 0. So I'm left with d by dt of phi plus 1/2 v squared equals minus p over rho minus big phi. And we'll talk about what big phi is. I'll get rid of big phi in a second. Is there anything else I need to say about it? Does this make sense to everybody? Does everybody see how I got here? Holler if you don't. So this is dv dt. This is the v dot grad v term. This one's hard to see in your head, but it comes from a vector identity. Here's my grad p, and this is my acceleration. We just got rid of the gradient because we get to do that now. Only works because it's incompressible and adiabatic, but that's okay. That's usually how things are. Okay. Let's leave all this. Let's go to this other board. All these things. Go to this other board. I guess that's as far as you go. Let's get everybody on. So, okay. Okay, and what we've got is two states. We have rho prime and u prime at the top and rho u on the bottom. I don't know what density or velocity are. We're going to keep those totally generic and make it more complicated in a minute. But we know that we have this interface here. And we're going to call the height of this interface c. That's this distance here. And what do we know? C is well behaved. interface height. We're going to call this Z equals 0 is our equilibrium condition. This is the middle of interface. So what do we know? I know that Xi moves with the fluid. And I know that across C, pressure is constant. Across C. Okay, so this bit here, C moves with the fluid. What does that mean? There's a number of things. Okay, so from 2, let's see, what can we say? So dx dt is what? Well, if we just expand out what this derivative is, this is the full derivative. So that's partial C partial t plus u partial C partial x. So our background solution is rho prime u prime, and our background solution is rho u. So that's our constant solution. So we're going to say that dx dt is just partial x dt plus u partial x du. This is just the convective derivative. Also, we know that this is the velocity, right? Dx dt is the z velocity. So this is also minus d phi dz. We're going to need this, so I'm going to write it up here. Dx dt equals partial c partial t plus u partial c partial x equals minus partial phi partial z. This is how phi behaves, so the vertical velocity, so this is vz. We can write this in a couple different ways. Oh, I need you to write this as a full derivative. Everybody happy with that? This is vz of the interface. Not the velocity in this fluid up here or this fluid down here. Oh, well, better be the. Okay, we'll come back to that in a second. This is the interface. I can also say, because the interface is the same on both fluids, I can also say that equals partial c partial t plus u prime partial c partial x equals minus d phi prime partial z. If I think about the interface's velocity as the velocity of this fluid on the top, that gives me this equation. And if I think about it as the velocity of the fluid on the bottom, that gives me this equation. And they're related to each other. So I know that these two equations have to be equal to each other. We'll come back to that first in a second. Okay, so we need a couple of things. We'll come back to this in a sec. So we need two other things. One is the fact that phi equals minus ux plus phi 1. This is how I'm perturbing the fluid. And similarly, phi prime equals minus u prime x plus phi 1 prime. So phi naught equals ux. Because I know that d phi naught dx minus equals u, the velocity. Remember, big U is the velocity, yeah.
So is this similar to what you did with the deltas?
This phi 1 is like what I did with the delta, yeah.
Okay.
So this is phi, and then we're perturbing it here, yeah, with phi 1. Now it's a little different because I'm not parameterizing it by delta, I'm parameterizing by phi 1. So in doing this, you have some freedom with what the small thing is. You have freedom with how you write it and how you do the derivation, and there's a bunch of different ways that work to get you the same derivation. So you could say, if I've got rho, v, and p, I could perturb it as rho goes to rho naught plus rho 1, and v goes to v naught plus v1, etc. Or I could say rho equals rho naught plus delta rho. Common thing we'll do, and then you can treat delta as a variable or delta rho as one thing. That's just the name of the tiny little thing. Or I could say rho equals rho of 1 minus 3 delta, for instance, if I'm parameterizing something else. So there's a couple different ways that you can set these up. Okay. So I'm going to perturb my potential flow in this way. So I've got ux, that's my bulk flow, and then phi 1 is my perturbation. And the other thing that I need is now we're going to do some Fourier business. And we're going to assume that, I'm just trying to decide where I put all my objects on the board. So we'll say that C1, that's my, I guess I call it C1 here. I don't think that I need to separate that. The book uses a 1 on C. I'm going to leave it off because I don't think I need it. A, that's some amplitude, e to the I k x minus omega t. And then phi 1 equals, we'll call this C, e to the I k x minus omega t. Oh, I got two variables. Oh, I'm sorry. I haven't needed it yet. In everything that I'm doing, the vertical component is z, and y is coming out of the board. I hope that shouldn't change anything that you've done so far. C doesn't have any information about the vertical quantity. It's just kx minus omega t, but phi 1 exists, this only exists at that interface. But phi 1 exists in all space. Yeah.
What is C?
C is a constant. So this is my amplitude. So I'm gonna write things a lot as f equals some number e to the stuff. And right now this is just the number part. Now in the stuff, so C is a constant, A is a constant. Kx minus omega t minus kz. Uh-oh. I gotta do that again. Why do I gotta do that again? Okay, that's my amplitude. E to the I, kx minus omega t. But the vertical component may or may not oscillate. So that doesn't get an I. Now, if it turns out that it needed an I, one will appear. I'll get a square root of a negative number somewhere in here for my equation for k. Now the other equation, phi 1 prime equals c prime e to the I, same business, kx minus omega t, but I want that negative, and I want this one positive. Remember, phi prime is the above, phi is below plus. I wrote it backwards. This is the equation that's on top. It gets a minus k because we want phi to fall off to 0 at k equals infinity. Now again, if I didn't make that assumption here, it would show up when I try to enforce the boundary conditions. I'm just just know that I'm going to need to do this in the future. So my assumption about phi is that it's got an oscillating part and an exponential part. The difference is this I. So we'll assume these, and then we'll drop these three equations into,
So is the k on z the same as the k on x?
That's a great question. I didn't answer that yet, but I should have. It is. It doesn't have to be. So far I haven't said anything. So right now, kx and kz are different. So far I haven't said why they should be the same. Why should be the same? Okay, so I know that grad div v equals 0. That's how I started here. What does this mean for the potential? Because grad phi is v, del squared phi equals 0. There's a minus sign, but it doesn't matter. So del squared phi equals 0. That's super important. What this means is d squared phi dx squared plus d squared phi dz squared equals 0. Now I'm making this assumption that they're going to behave like that, and it's not really an assumption, it's a thing that I'm allowed to do. I can say that because there is an equivalence that I get to use. It's not that I'm making anything up, it's that I'm allowed to do this. These become Fourier transforms. So when I drop these into here, the x becomes a k squared minus phi, and then this one becomes a minus kx squared. This one becomes a minus kz squared phi equals 0. So I get a kx from the x derivative and a kz from the z derivative. This one is actually, and so when I move this over here, you see that kx has to equal kz. There's a sign because these are squared, but the wave number in k, the x has to equal the wave number in kz in magnitude. And I'm going to force the sign by saying I know how they need to behave. Does everybody follow that?
Does the minus sign come from the I squared when you take this?
Yeah, this minus sign comes from this I squared.
And then would the kz be positive?
Yeah, it should be positive, but again, we've got this plus or minus ambiguity because they're squared. Actually, this one has to be positive because when I put that one over there, I want them both positive. I don't want a negative sign because then I have an imaginary number. Okay, so that's a good question. So now I'm just going to use k. Okay, now I'm going to drop these into here. And all we're going to do is we're going to have an equation for, so what these equations say is that the interface moves. That's all it says. The interface is moving with some velocity that it has. It has some velocity that the fluid is giving it. So all this says is that the interface is moving with the fluid. We drop these into that equation and we're left with some nice simple math. So we're left with, do I see which comes from which? Yeah, so I've got two equations up here. One for the top and one for the bottom. And this is going to give me I times minus omega plus k u prime a equals plus k c prime, and I times minus omega plus k u a equals minus k c. Okay, let's map this out. dx dt. Dx dt is just going to bring down a minus I omega and an a. And then we'll have this same oscillating thing that we get to get rid of. The u dx dx gives me a k times u and an a. And then the minus d phi dz is going to give me a k times c. And then I'll have the same thing, but without the primes, and then the other sign on the k term. So this is from my z derivative, this is from my x and y derivatives. And now we have things that don't resemble our original equations at all. We'll do something in a second that really muddies the water. Okay, we need these. We'll use this board again, even though it's always a terrible idea. It's my wishful thinking. Okay, these things, these are things that we'll need. Okay, where did these come from? They came from the interface is moving. They came from Fourier analysis. They came from potential flow. Okay, so now here, let's go back to whatever Euler's equation has now become. d phi dt plus 1/2 v squared equals p over rho minus that's a terrible p. Phi is c times g. G is my gravitational acceleration. This is the same as saying mgh. Remember doing mgh and all of your things falling off of, rocks falling off of buildings, you always have an mgh term, right? This is the same thing. This is just h. This is just g. So other ways I can come to this equation, but we'll do it this way. Minus c times g. So now I need to plug in, yeah.
I'm confused about the vector.
This, oh, this. Oh yeah, I'm sorry, that should be, right. Thanks. G is just the magnitude of the gravity. So now we plug in our Fourier analysis, our Fourier business again. And, let's see, because we've got phi there, and we've got v, and we're left with, let's get an equation for p. That's actually what we need to do. P equals what? Rho dt phi minus I minus 1/2 rho v squared plus g times c. That's got to go the other side. No. You go over there. You stay there. You come over here. You go. Everybody's in.
Professor?
Yeah.
If we assume that v was negative gradient of phi, should it not be a negative in front of the del t?
Yeah, probably. There's minus sign there. Because, as he said, we went from here to here, and I dropped this minus sign here. Or I dropped a minus sign here. Actually, there and there. So this is the same on both sides of the equation. So, so at the interface, P equals P prime. Then we drop in our Fourier modes, and we're left with this. We've got rho times, let's see, minus I times minus omega plus ku times g times a equals rho prime times minus I minus omega plus ku prime. Oh, C, I missed a C. Can't read my handwriting. times C plus GA times C prime plus G times A. Okay. This equation doesn't tell us anything all that interesting or useful, so the only thing that we did is this. This is just doing this. So now watching me do algebra is boring as hell and not very useful. We take this and that and figure it out and get an equation for omega. Omega over k equals rho, okay, this is something that is useful. Rho u plus rho prime u prime divided by rho plus rho prime plus or minus, here's a giant thing, g over k, rho minus rho prime over rho plus rho prime plus rho prime u minus u prime squared over rho plus rho prime squared. All of this to the 1/2. This equation is important, so you should write this one down. Watching me do the algebra is not as nearly as fun as doing the algebra yourself, but you get here. So okay, let's go recap before we do anything else. Oh, and take a detour. Actually, I'll show you the answer before I take a detour. So we'll close with the demo because I got like 10 minutes left. So how did we get there? How did we get here? So we started with that.
What is the term next to in the parentheses? The far left term in the parentheses. Yeah.
G over K.
Okay.
Rho minus rho prime over rho plus rho prime. Let's recap what we did. So we started with Euler's equation. We then assumed incompressible so we could use the potential. We then rewrote Navier-Stokes to be like this, got rid of viscosity, so now we have Euler's equation. And simplified this guy a little bit to this. Okay, so now we have a constituent equation. It's still Navier-Stokes equation. We just cleaned it up a little bit and made it a little bit more useful. Then, should have done this in order on the board. If I had the ability to plan my board so that it was in order, that would be really cool, but I don't. We just wrote down the interface has to move with the fluid. That's all we wrote down. But we put some math with that. And then we did some Fourier analysis. And then we assumed that the pressure is constant across the interface. It's a couple of steps that we got to go through, but then we do a bunch of algebra and we're left with our dispersion relation. So now this dispersion relation has a lot of going on. So let's talk about it. And I'm going to write it again more cleanly. Omega over K equals rho u plus rho prime u prime over rho plus rho prime plus or minus G over K, there's another K, rho minus rho prime over rho plus rho prime. This all this stuff on this side is in a square root, right? So your brain should say, hey, I got a minus sign under a square root. This is going to blow up on me. See that? See how I can have this blow up on me. Plus rho prime, u minus u prime squared over rho plus rho prime squared. All of this to the 1/2. Okay, so the simplest thing I really appreciate that in the text of the book he threatens. Oh, didn't have the camera on. That's fine. He threatens you with homework problems, by saying, "Okay, this isn't actually completely right. It's a homework problem." I think it's a good homework problem, so I might assign it. The basic idea is do this, but do it if there's a floor of the ocean. So if there's a floor in the ocean, then that changes the boundary conditions and changes the results a little bit. This is how water waves work in the ocean. But if we just simplify and say, okay, my boundary condition is infinitely far away, so very deep water, we're going to assume that u equals u prime equals 0, so that the water is just sitting there, and rho is bigger than rho prime, so that it doesn't fall out of the sky. So heavy is underneath light. So what does that mean for this? That means this first term goes away, this last term goes away, and we're left with omega over k equals plus or minus g over k rho minus rho prime over rho plus rho prime. Get rid of that. So this is the dispersion relation for deep waves, for deep water waves. If we have shallow water waves, then we get a hyperbolic tangent function. But you can see that it's dispersive. Omega over k depends on k. So this is the phase speed, remember? It depends on the wavelength. Bigger waves travel faster than smaller waves. Is that right? Smaller waves travel faster than bigger waves. This k, if the wave is small, k is big. Yeah.
So what would happen if rho is equal to rho 1 or rho prime?
That's a good question. Then I have 0. Then you don't have any kind of interface wave, because then you don't have much of an interface at all. You can't have a gravity wave that way. So this is a gravity wave. And that's not a gravitational wave. These are different things. A gravity wave is what water does. A gravitational wave is what the fabric of space does. This is much more violent than this. So be careful when you're searching. And now, when I search for gravity wave, Google decided that it was going to show me only results of gravitational wave, because Google sucks now. Anyway, I have a soapbox that I can get on about how shit Google has become in the last 2 years. So anyway, gravity waves. So this is a gravity wave. Now, if rho is bigger than rho prime, then this is imaginary for every k. So if you put the heavy fluid on top of the light fluid, it collapses. And it's unstable all the time. Oh, wait, did I talk about what that means? I guess maybe I didn't. So what happens? What happens if rho prime is bigger than rho, then this whole thing is I times some number. It's imaginary. I have all these things that look like I omega t. So if I put something imaginary in here, the i's cancel out and I get something that either blows up exponentially or decays exponentially. Now, decays exponentially is useful. We want to know about that. Blows up exponentially, you really want to know about, because that's problematic. So if I have heavy fluid on top of light fluid, things fall. You want to see it? Yeah, do you guys want to go do a demo? I'm going to pause the video because I'm not carrying the video with me. It's demo time. I'm sorry you miss it.